A crack the width of a single human hair running across a bridge that carries 40,000 cars a day. Now picture that crack closing itself, on its own, with no worker, no truck, no lane closure, like a scab forming over a cut on your skin. That is not science fiction. That is happening right now on a bridge in eastern China, and by the time this video ends, you will understand exactly how concrete learned to heal itself, why it took the world this long to pull it off, and what it means for every road, tunnel, and skyscraper still standing decades from now. If stories about engineering that sounds almost too strange to be true are the kind of thing that keeps you curious, sticking around and hitting subscribe means you will not miss the next one, because there is a lot more where this came from. Concrete is the most used man-made material on the planet. More of it gets poured every single year than steel, wood, and plastic combined, which means the story of concrete is really the story of almost every bridge, sidewalk, dam, and apartment building you have ever walked past without a second thought. It looks permanent, it feels permanent, but underneath that gray, unchanging surface, concrete has always had a hidden clock ticking inside it. And for most of the last century, nobody could figure out how to stop that clock without tearing the whole thing down and starting over. For over 100 years, concrete has had one enemy it could never beat, and that enemy is water. Concrete looks solid, but at a tiny scale it is full of pores, like a sponge that has been squeezed hard but never fully closes up. Water sneaks into those pores. When it freezes, it expands and pushes the concrete apart from the inside. When it carries road salt or sea air, it eats away at the steel bars buried inside the concrete, called rebar, which are the bones that give concrete its strength. Once those bones start to rust, they swell, and swelling steel cracks the concrete around it even more. It becomes a slow, spreading wound that starts smaller than a fingernail and can end with a chunk of bridge deck falling off years later. Engineers have known about this problem since the days of the earliest reinforced concrete bridges, back in the late 1800s. For most of that history, the only fix was to watch and wait. Inspectors would walk bridges with a hammer, tapping the surface and listening for a hollow sound that meant trouble underneath. Then crews would drill out the damaged section, patch it, and hope the patch held. It rarely held as well as the original pour. Patches are like stitches on a wound that never fully closes. They cover the damage, but they do not restore the original strength. And over time, the same spot often fails again. Inspection itself is slower and more dangerous than most people realize. On a large bridge, a full inspection can mean shutting down lanes, hanging workers off the side in a basket, and running sensors over every meter of the structure by hand. Some of the most important cracks are not even on the surface, where a camera can see them. They form deep inside the concrete, around the rebar, invisible until the damage is already serious enough to show through the paint. By the time a crack is visible to a person walking by with a flashlight, the damage underneath is often years old already, quietly growing the whole time nobody was looking. And the timing problem makes everything worse. A hairline crack today might take 5 years to become a real structural issue, or it might take 15, depending on rainfall, temperature swings, and how much salt gets used on the road in winter. Engineers cannot inspect every bridge every single week. They have to guess which structures need urgent attention and which ones can wait, and that guessing game, spread across tens of thousands of bridges, is exactly the kind of problem that eventually forces engineers to stop reacting to damage and start looking for a way to prevent it automatically instead. The scale of this problem in China is hard to picture, so here is a comparison. China has built more bridges in the last 20 years than most countries have built in their entire history, including thousands of long-span bridges, elevated highways, and high-speed rail viaducts. Maintaining that much concrete is like trying to keep a paint job fresh on a city the size of Texas, except the paint is holding up bridges over rivers, valleys, and city streets. Every crack that goes unnoticed is a small bet against gravity. Engineers in China needed a way to catch the smallest cracks before they became the kind you can see with your eyes, and ideally, a way to make the concrete fix those tiny cracks without a human ever climbing up there. So why did it take until now to solve something this basic? Because closing a crack from the inside means getting a material to somehow know it is damaged and then respond, without a battery, without a sensor, without anyone flipping a switch. That is a strange kind of intelligence to build into a rock-like material that has no moving parts. It sounds almost like asking a brick to grow its own bandage. Getting there took a mix of biology, chemistry, and years of trial and error, and that is exactly where this story gets interesting. Think about how your own body handles a small cut. You do not consciously decide to heal it. Blood reaches the wound, a chemical process kicks in, and a scab forms to seal the opening and protect what is underneath. Nobody has to press a button. The system is built to react automatically the moment there is a break in the surface. Chinese researchers, working with ideas already being tested in labs in the Netherlands and elsewhere, asked a bold question. What if concrete could do something similar? It is worth sitting with how strange that question really is. Concrete is not alive. It has no nervous system, no blood, no way of sensing pain or damage the way your skin does. Building a repair response into something that lifeless meant engineers had to borrow tools from a completely different field, biology, and figure out how to make living organisms survive inside a material that is normally about as hospitable to life as drinking a glass of drain cleaner. That is the leap that had to happen before any of this could leave the drawing board. The answer they landed on has a few different approaches, and it helps to walk through them one at a time, like separate tools in the same toolbox. The first approach uses tiny capsules mixed into the concrete when it is first poured, similar to how a pain reliever capsule holds medicine inside a shell until your stomach breaks it down. These capsules are packed with a special adhesive or a sodium-based solution. They sit inside the concrete doing nothing for years, harmless and inactive. But when a crack forms and runs through one of these capsules, it breaks open, exactly like a water balloon popping when it hits the ground. The liquid inside spills into the crack, reacts with the surrounding material, and hardens into a solid filler, sealing the gap from within before it can widen. The second approach is stranger and, honestly, more amazing. Researchers mix dormant bacterial spores into the concrete along with a food source for those bacteria, usually a compound based on calcium lactate. These spores can survive locked inside dry, alkaline concrete for years, similar to how a seed can sit dormant in dry soil until it finally gets water. When a crack lets in water and oxygen, the spores wake up. They feed on the calcium compound, and as a natural byproduct of their digestion, they produce calcium carbonate, which is essentially the same mineral that makes up limestone and seashells. That mineral fills the crack and hardens into something almost as strong as the surrounding concrete. The third approach uses microscopic mineral additives, sometimes combined with a network of fine capillary channels, that pull in moisture and trigger a chemical reaction similar to how the concrete originally cured when it was first poured. Picture it like a tiny factory inside the material that only turns on when water shows up uninvited, then shuts itself back off once the leak is sealed. What makes the bacterial method especially clever is how patient it is willing to be. A bacterial spore is basically a bacterium that has shut down almost every function except survival, wrapped in a tough protective coat, waiting for the right conditions to come back to life. Some spores found in nature have stayed dormant for decades, even centuries, in dry or harsh environments. Engineers picked strains that specifically thrive in alkaline conditions, since normal concrete is roughly as alkaline as diluted bleach, an environment that would kill most ordinary bacteria within minutes. That single detail, choosing a bacteria species tough enough to survive inside wet cement in the first place, took years of testing dozens of strains before researchers found ones that could actually make it through the pour and still wake up years later. Getting the timing right mattered just as much as picking the right bacteria. If the healing agent activates too early, before a real crack appears, it gets wasted, sealing nothing. If it activates too late, the crack has already widened past the point where the agent can bridge the gap. So the whole system is built around a simple rule. Nothing happens until water physically touches the healing agent through an actual break in the material. No water, no reaction, no matter how much time passes. That built-in trigger is what makes the process reliable instead of random, the same way a smoke detector does nothing until it actually senses smoke, not before and not after. Put these three approaches together and you get concrete that behaves less like a dead slab of rock and more like living tissue with a built-in repair crew on permanent standby. It does not prevent every crack from forming. What it does is stop tiny cracks, the kind you cannot even see without a microscope, from ever growing into the kind of damage that shortens a bridge's life by decades. Picture thousands of these microscopic repair kits scattered through a single bridge deck, each one asleep, each one only reacting to the exact spot where it is needed, and never anywhere else. But how do engineers know it is actually working, out in the real world, and not just in a lab dish under perfect conditions? That is where the story moves from theory into steel, concrete, and real traffic. The research behind this technology has been developing for more than 15 years across several Chinese universities, with Southeast University in Nanjing and Zhejiang University among the most active centers studying self-healing and bio-based concrete. Researchers there have published detailed studies on bacterial self-healing concrete, measuring how much of a crack's width can seal itself and how much the material's strength recovers afterward. In lab conditions, some of these studies have reported healing efficiencies in the range of 70 to over 90% for hairline cracks, meaning cracks that started out roughly 0.1 to 0.4 millimeters wide, thinner than a sheet of paper, were largely sealed shut within about 4 weeks of exposure to moisture. China's Ministry of Transport has also pushed self-healing and long-life concrete research as part of its broader push to extend the service life of national infrastructure, with pilot standards and technical guidelines developed through the China Academy of Transportation Sciences. Funding for durable concrete research has come through China's National Key Research and Development Program, with individual university projects receiving grants in the range of several million yuan, aimed specifically at scaling lab-tested self-healing formulas into materials that can be mixed at a normal concrete plant and poured using normal construction equipment. That last part matters more than it sounds. A material that only works in a small lab batch is a curiosity. A material that a normal concrete truck can pour is an industry-changing tool. Cost has been one of the biggest hurdles engineers had to justify. Early versions of bacterial self-healing concrete could cost anywhere from 20 to 50% more per cubic meter than standard concrete, largely because of the price of processing and protecting the bacterial spores so they survive the extremely high alkalinity of wet concrete, which is normally hostile to almost any living organism. Researchers have been working to bring that premium down by using cheaper spore protection methods, such as encasing the bacteria in expanded clay particles or diatomaceous earth, which act like tiny protective shells, similar to how a turtle's shell protects it while still letting it move and breathe. Academic partnerships have played a bigger role in this story than most viewers would expect. Material science departments at Southeast University and Zhejiang University have run joint testing programs with civil engineering institutes, publishing peer-reviewed papers that track healing performance across dozens of concrete samples, cured for different lengths of time, exposed to different levels of moisture, and cracked under carefully controlled laboratory conditions using hydraulic presses that can apply thousands of newtons of force to a single test block. That kind of repeated, documented testing is what separates a promising lab trick from something an engineer would actually be willing to put their name on for a public bridge. The China Academy of Transportation Sciences has also worked on drafting technical guidelines for how self-healing additives should be tested, measured, and certified before they can be used on a national highway project, since without a shared standard, every province and every construction company would be left guessing whether a given product actually works as advertised. Building that kind of standard takes years of comparing lab results against real field data, which is exactly why this technology has moved carefully instead of being rushed straight from a research paper onto a bridge carrying commuter traffic. So, the lab numbers look promising, but has this actually been tested on something real? Something with cars driving over it every single day? Yes, and this is where the idea stops being a research paper and starts being a bridge you could actually stand on. Trial sections using self-healing and crack-resistant concrete formulas have been built into pilot projects on highway bridges and pavement sections in provinces including Jiangsu and Zhejiang, two of the regions most active in applying new concrete technology at scale. In one widely cited pilot program, engineers applied a self-healing surface treatment and internal bacterial additive to a bridge deck section, then monitored it over roughly 18 months of real traffic exposure, including heavy trucks and seasonal freeze-thaw cycles. Inspection teams reported that surface microcracks, which would normally have required manual sealant application, had closed on their own, cutting the need for that specific type of manual maintenance work on the treated section by a reported figure of around 60% compared to an untreated control section nearby. Separately, research teams have tested self-healing concrete in simulated marine environments, since bridges and structures near China's coastline face some of the harshest conditions anywhere, with salty air and seawater attacking rebar far faster than in dry inland regions. In these tests, treated concrete samples showed significantly slower chloride penetration, meaning the salt took much longer to reach the steel rebar inside, which is the single biggest factor in how long a coastal bridge lasts before it needs major structural repair. Some trials reported chloride penetration reduced by roughly 40% compared to standard concrete over a comparable testing period. The freeze-thaw testing tells its own story too. In colder parts of China, bridges go through dozens of freeze and thaw cycles every single winter, and each cycle is like squeezing a sponge full of water and then letting it expand as ice, over and over, thousands of times across a structure's life. Standard concrete samples in comparison testing showed a steady buildup of surface flaking and micro-cracking after repeated freeze cycles in a lab chamber. Treated samples with self-healing additives showed noticeably less surface degradation after the same number of cycles, largely because cracks that would normally widen with each freeze were being sealed before the next cycle ever hit them. None of this means every bridge in China is already made of self-healing material. Most are not, at least not yet. What these pilot projects prove is that the idea survives contact with the real world, with real weather, real trucks, and real salt, not just a controlled lab environment where everything is perfectly measured and nothing unexpected happens. And every pilot section that holds up under real conditions is one more piece of evidence engineers can point to the next time they need approval to use this material on a bigger, more critical structure. Zoom out for a second, because the implications here go far beyond one bridge in one province. Infrastructure maintenance is one of the single largest ongoing costs any country faces, often larger than the original cost of building the structure in the first place, once you add up decades of inspections, patch repairs, and eventual replacement. If self-healing concrete can meaningfully extend the working life of a bridge, even by an extra 10 or 20 years, the savings across an entire national highway network could reach into the billions of dollars. Because you are not just saving on materials, you are avoiding traffic shutdowns, avoiding emergency repair crews, and avoiding the risk of a structure failing without warning. There is also a competitive angle here that is impossible to ignore. Countries including the Netherlands, the United States, and the United Kingdom have all funded their own self-healing concrete research, some of it dating back even earlier than China's push into the field. What makes China's approach notable is less about who invented the underlying chemistry first, and more about speed of real-world deployment. China builds an enormous volume of new infrastructure every single year, which means it has more opportunities to actually test experimental materials on real bridges, real tunnels, and real high-speed rail lines, rather than leaving a good idea trapped in a university lab for another decade. In a field like materials science, being able to test at scale quickly is its own kind of advantage, maybe even the most important one. Think about what this could mean for cities built in flood zones, for coastal highways battered by typhoons every year, for mountain roads where a single crack can widen into a landslide risk within a few rainy seasons. A material that quietly repairs itself before a human even notices the damage is not just a convenience, it is a way of buying time and safety in exactly the places where both are hardest to guarantee. There is a workforce angle here too, one that rarely gets talked about. Bridge inspection and repair is dangerous work, done at height, over water, sometimes over active traffic lanes with cars passing just feet away from a worker on a platform. Every crack that heals itself is a crack nobody has to hang off the side of a bridge to fix. Reducing that kind of manual repair work does not just save money, it removes real physical risk from the people whose job it is to keep these structures standing. As self-healing materials expand into tunnels, dams, and even the concrete piers that support offshore wind turbines, that safety benefit multiplies across every structure that no longer needs a human to climb out and patch a hairline crack by hand. There is also a climate angle worth pausing on. Producing cement, the key ingredient in concrete, is responsible for a significant share of global carbon emissions, since making it requires heating limestone to extremely high temperatures. Every time a bridge needs a major repair or an early replacement, that means pouring more fresh concrete, which means burning more fuel to make more cement. A material that extends a structure's working life by even a decade is not just an engineering win. It is fewer tons of cement that need to be produced at all over the coming century, which is exactly the kind of quiet, unglamorous change that adds up across an entire country's infrastructure network. Other countries are watching closely, and some are already racing to keep pace. Research groups in the Netherlands, at Delft University of Technology, were among the earliest to publish work on bacteria-based self-healing concrete, and teams in the United States and South Korea have run their own pilot programs on smaller structures like sidewalks and parking garages. What sets China's trajectory apart is not a single breakthrough moment, it is the sheer number of real structures available to test on, paired with a funding pipeline willing to move promising lab results toward actual highway pilots within a handful of years, rather than leaving them to sit in an academic journal for a decade. In a technology race like this one, the country that can move fastest from lab bench to real bridge deck tends to end up writing the standards everyone else eventually follows. Will self-healing concrete completely change the way bridges get built within our lifetime? Or will it stay a specialized tool reserved for the most critical structures? That is still an open question, and the answer will likely come down to how fast the cost keeps falling over the next few years. Now, here is where it is worth being honest, because this technology is impressive, not magic. Self-healing concrete is not a cure for every kind of damage. It works best on very small cracks, generally under 0.5 millimeter wide. Once a crack gets wider than that, especially the kind caused by a genuine structural problem like an overloaded bridge or a poor foundation, the self-healing agents inside the material usually cannot bridge the gap fast enough, and traditional repair is still needed. In other words, this technology handles the small, slow damage that would otherwise sneak up on engineers over years, but it is not a replacement for good design, proper load limits, or regular human inspection. There is also the question of how long the healing agents themselves last. Bacterial spores and chemical capsules are mixed in once when the concrete is first poured, which means their supply is not infinite. Most current formulas are designed to remain active and useful for roughly 20 to 30 years, which covers a large share of a structure's early life, the period when it is most exposed to fresh cracking, but engineers are still studying exactly how healing capacity fades as concrete ages closer to 50 or 60 years old. Cost remains a real barrier too. Even with prices coming down, self-healing concrete is still more expensive up front than standard concrete, and for now it tends to be used selectively, on high-value structures like major bridges, rather than on every stretch of ordinary road. Wide-scale adoption will likely depend on continued cost reduction, and on more long-term data proving the savings on maintenance genuinely outweigh that higher starting price over a bridge's full lifespan, not just over the first year or two of monitoring. There is also the challenge of proving this technology works over the kind of timeline that actually matters, which is decades, not months. Most of the pilot programs discussed here have only a few years of real-world data behind them. A bridge is expected to last 50 years or more, so engineers are essentially making an educated bet, backed by strong lab results and promising early field data, that the healing performance seen in year 1 and year 2 will hold up in year 20 and year 30. That is not a flaw unique to this technology. Every new construction material goes through this same waiting period, but it is worth being upfront about, instead of pretending the long-term case is already fully proven. And finally, there is a quieter risk that engineers take seriously, which is over-reliance. A bridge with self-healing concrete is still a bridge that needs regular human inspection, weight limits, and maintenance planning. The danger of any technology that quietly fixes small problems in the background is that people start trusting it to catch everything, including the kind of large structural damage it was never designed to handle. The engineers behind this technology are careful to describe it as one more tool that extends a structure's life, not a replacement for the inspectors, sensors, and maintenance schedules that have kept bridges safe for the last century. So here's the core idea, stripped down to its simplest form. Engineers in China found a way to hide a tiny, dormant repair crew inside ordinary concrete, using bacteria, capsules, and minerals that only wake up when water sneaks into a crack. And in real pilot tests, that hidden crew has already cut maintenance work on treated sections by more than half. It is not finished technology, and it is not cheap yet, but it is one of the clearest signs yet that the materials holding up our world are starting to think a little more like living things. If this kind of engineering leaves you wanting more, liking this video and subscribing costs nothing, but helps this channel keep digging into the breakthroughs most people never hear about, and turning on notifications means you will be there the moment the next one drops. If you could pick one piece of infrastructure near where you live to get this kind of self-healing upgrade first, a bridge, a tunnel, a stretch of highway, which one would it be, and why does it need it more than anything else around it?